给我先。哎，
马来西亚人。
你们那一包一包是哪里买的？有吧？又买这样多，对。
每个人变早安帅哥，早安妹子一样说。
那跟 KL 不是一样？靓仔靓仔。
都可以。就一起来。
干嘛？你是超厉害了吗？这么厉害？
然后第三几个听到我玩，我
走啊，康平。Let's go, let's go。
你以为你还要不要进方了？
我的。
有些比他进攻的时间。
我觉得那个 Perman 比较切吧。
切。
没有 ，the thing is that the time is the same.
What time?
She connects with him and she connects with me.
啊，把你的故事拎在一起。
地震度啊，现在也不是地震度。
That's cool。
那个可是。
没有，它是 parallel story。
Time.
Parallel story 啊。
At the same time.
对啊，对啊，对啊。
还要才算2个1个。
喂喂喂。Hello, hello, testing. All right, let's start. So today we aim to at least state Hilbert Nullstellensatz, if not prove it. At least 就至少一定要讲到的。
当然是你说这种话，这个都达不到。
希望达得到。Okay, so let's work towards the goal. All right, so yesterday we defined a affine algebraic set, right? So what's the affine algebraic set means? So where you take the affine algebraic set from? So it's a subset. Yes, subset. Let's call it. What do you want to call it? Let's call it. What do we call it? What's the notation we use? Or any special notation you want to use? Let's call it V, huh? V. Okay, let's take V. Subset V. A. Last time we used A. Y. Okay. Never mind, we use V then. So subset V in A N K here is an affine algebraic set if there exists a subset inside the we call it a dual space here. So the polynomial ring of n variables such that this V here is the zeros of all the polynomials in P. Okay, and yesterday we proved that the the common zeros of T is actually equals to the common zero of the ideal generated by T. Right? This is what we proved yesterday. Okay. Okay. And yesterday we went through a bunch of examples of R-prime algebraic set, and we proved some properties on R-prime algebraic set, namely when you have a subset inclusion of your function space, how does it reflect on your zero set? Okay, and then when we collect all these properties together, actually it forms a topology. Okay, it forms a topology where you take the open set to be the complement of the R-prime algebraic set. Okay. Or if you define it as a closed set topology, then you literally just take the R-prime algebraic set. Okay, let's see some non-examples of algebraic set. So let's look at some non-examples. Starting from now, I try to write less. I try to draw more and try to list more points. Okay, because too many little things need to write, so we don't want to put too much detail on them. But we will provide it in the lecture note. So, one first example is the open ball. Okay, so if you look at this open ball in let's say CN here. Okay, so what I draw is just C2, but I mean R2. But if you imagine an open ball in CN, it's not an algebraic set. Okay, and if you take similarly a closed square here, it's also not an algebraic set. Well, we take open ball. Well, one claim you can prove is there's no non-trivial algebraic set in C2 can have interior point. I guess you can do it for CN. Maybe you can generalize it to CN. There's no non-trivial algebraic set in CN can have interior points. Okay, so how do we talk about interior points last time? You did in MA2 or not? Interior point. How do you define interior points? Huh? You do it 3 times. How do you define interior point? Campaign. Yeah. Yeah, sure. Open ball, yes. So everything. So if a point is an interior point of some set A, let's say set A, what does it mean? There's a ball inside a set, there's an open ball inside a set A that contains the point. Okay. Yeah. Okay. Next. Also, if you look at the set of invertible matrix, GLN, this is also not an algebraic set. What is GLN? GLN is actually the m by n matrices portion out, take away. Okay, take away on these matrix. So all the matrix in n by n matrices such that the determinant of M is 0. Okay. set minus. Okay, yeah. So you can see that when determinant m equals 0, this is a bunch of algebraic equation here. Okay, so it defines a affine algebraic set. Okay, and then you take the complement is open. So you can write it as a zeros of some polynomials. Okay, what else? If you consider like what we did yesterday, right? So if you consider the graph of transcendental function, okay, also not algebraic. Maybe you can try and show this. For example, the graph y equals to e to the x, the exponential graph. Okay, it's not algebraic as well. Okay. Okay. You can try and show it. Yep. Okay, continue. So once we have a topology on a space, right? So one thing you could ask is, can I split out my subset, okay, using the open set, okay, or the closed set? Okay, so we'll define that a non-empty subset of a topological space X is irreducible. It is irreducible if it cannot be expressed as the union, okay, of two subsets. So y1, y2. So this y1, y2, right, must be proper. Okay, must be proper. You cannot say y equals to y union y. A very, I know, stupid. So we want to split it into two proper subsets. And each of them have to be closed. Okay, in this case here, we will define it to be closed since we really care about the closed set in the topology. But if you do a bit more general topology, right, actually you can see that it is equivalent. It says that y cannot split into two proper open subset. Okay, it's equivalent actually. Two is equivalent to y here, y1, y2 are two proper open subset. Okay, these are equivalent. So later on in the general topology class, we actually will prove this. Yeah. So for this class, you can assume it if you're gonna use it. So we will go in between them. I don't think we have an option to go one close, one open. Either two close or either two open. Okay, both close, both open. There's one convention here is the empty set is not considered to be irreducible. So when we talk about irreducible subset, we don't care about empty set in this case. Okay. All right. So for example, so what are the is A1 irreducible or not? Can you split A1 into two proper union of two proper closed set or not? What are the proper closed set in A1? Yesterday we proved. Finite set, right? Okay, so if you take two finite set together, what do you get? Still finite, but A1 got how many things there? Infinite. Okay, So we'll say that A1C is irreducible. Okay, because no matter what closed subset you union them together, you will still only get finitely many elements. Okay, but the whole space should be infinite. Well, maybe things could change if you move to a finite characteristic field, right? If you move to finite characteristic field, then it could be different because your element could be finite. Okay, but in this case here is C. Similarly, you can talk about R. All right. So now we're going to define the most important definition here. So we'll define what is called the affine algebraic variety. Or sometimes we simply just throw away algebraic. We will just call it affine variety. Okay, so what's the affine variety here? So affine variety is an irreducible closed subset of AN with the Zariski topology. Okay, so meaning these are the irreducible algebraic set. Okay. Meaning what? So these affine varieties is the building block. Okay, building block of your algebraic set. Okay, because if it is reducible, then we can write it as a union of irreducibles. Okay, so these are the building block. Okay, affine variety. So, well, if you look at an open subset of an affine variety here, then these are called the quasi-affine. Okay, quasi-affine variety. Towards the end, we will see the connection between these two. Okay. So I'll recall one lemma for you, which we're not going to prove it. It's a topology lemma. So if you have a closed set, okay, the following is equivalent. So if you talk about V is irreducible, then if you take any two open sets, okay, if you take any two open set, U1, U2, which is non-empty of V, okay, then we will have that their intersection is non-empty. Okay, if it is empty, what can you do? You can literally use this open set to open up your V. Okay, if it's empty, then you can use this open set to factor your V. Okay. Part 3. I think this notation, this word we haven't defined for you, right? So every open set that's not empty in V is actually dense in V. What does dense mean? Yeah, so that's one of the definition. So if you take the closure of U, it is V. Okay, so let's take that definition then. So this implies that U bar equals to V. But how to take closure here? Well, if you go down the streak of topology, right? So the closure just says that you add in all the limit points. Okay, you add all the limit points. Zariski topology has another definition. So another definition is if you take, so we haven't introduced the idea yet, but we will do it soon. So if you take the algebraic set, or not even algebraic set, just a subset of the affine space, you can look at the ideal, okay, of function that vanish from this point. So let's call it I have all the functions that vanish on the point as the way I have. And then what can you do? You got a function again. Then again you apply V on this function space. And so VIS. So again you go and find what's the zeros again that diminish on these function space here. Is it the same or not? Is it the same? Is it the same as you started with? Or you got more? Okay. Yeah. I think I'll put that into your tutorial later. Let you play around with the Zariski closure. Okay. So yeah. Okay. So maybe I put one line here for you. So proof idea here. So if you have U1 intersect U2, right? It's empty. What does this mean? You can take V slash U1 here. It's closed, right? Union with V slash U2 here also closed, right? These two should have non-empty intersection. But these two add together is just V. Okay, so basically you can use this two concept to split out your V. Okay. And the other thing is, so this is one part. Second part is, if U in V is dense, actually you can prove that. Actually, we'll prove this in a general topology. It means it will meet every non-empty open subset of V. Okay, so mix means here, means what? Means intersection. Okay, it will intersect. So if a set is dense in one set here, then this U here, right, will intersect with every non-empty open set. Yeah. So it's pretty important to say that this open set is non-empty because empty set is open. Okay. Okay. Yeah. All right. So probably we need this later. So we'll go into the realm of Hilbert Nullstellensatz here. So anyone know what Nullstellensatz means? Huh? Now it's zero. Stellen? Sat is theorem, right? Stellen? Set. Zero set theorem. Is it zero set theorem? Okay. So it's a theorem about zeros, basically. Okay. So this is given by Hilbert. You know who is Hilbert? Hilbert's face, Hilbert. Yeah, so Hilbert is quite famous in mathematics. I think he's like a modern Gauss, I guess. Modern Gauss. He also do a lot of area in mathematics. And then he asked a very famous question. I mean, he got a problem list. How many problems in the list do you know? 23, right? Okay, he got 23 problem he announced in one of the ICMs. Basically, I think all of them are proven. I guess they are proven in some sense, I guess. Yeah. You sure? I think it is solved, right? Huh? Okay. Don't know. You sure? I asked my supervisor any unproven one. He said proven already.
Just like hypothesis.
Oh, is it? Oh no, I mean that's undecidable already. You cannot prove from set theory. is a problem that you cannot solve reading the theory. Yeah. Okay, so it's a very interesting subject to look for. Well, I think maybe student council can discuss this. Very interesting question at this Hilbert problem. Okay, you can make a Hilbert week. Hilbert week 啊？没有，你要趣味一点，你不可以太那个，你要做点趣味。
Do you want to make a talk again about the Hilbert polynomials?
Okay, so we're gonna define for every subset of AN. Okay, the ideal, call it IY. It depend on this Y here. So this ideal will live in the polynomial ring with n variables. How do we define this? So this is very simple. IY is just all the function such that F will have P be 0 where P are taken from 1. Okay. As long as your F have zeros in Y. So the proposition again, similar to what we have for the zero set. If X is in Y, okay. So in this case here, which one has more point, X or Y? X has more point or Y has more point? Huh? X. X is a subset of Y. Which one have more points? Y, right? Okay. So how do you relate IY and IX then? Huh? Reverse again, 哈。怎么他这样多女朋友啊？他不闲的啦，他什么都可以。Less condition, IY, huh? Less equation, need to satisfy. 是不是？哎，是吗？我有讲错吗？IX 啊，是 IX 到这一个。哎，我讲错了，没有 IY 对啊。Less equation, okay, less function. So you have this subset inclusion reversing property again. Okay, on this IY here. Similarly, you could ask about what? Can you guess what's next? Based on what you know about common. Union and intersection. Where are we going to do that soon? Let's see. I think, are we going to do that? Not really doing that. Sorry, I or V. Yeah. Okay, so yes. So you can ask about the ideal of nothing. What is the ideal of nothing? Nothing? Something. Everything. It's everything. Okay, it's everything here. But the ideal of everything, got something. Just the zero polynomial. Yeah, nothing ever GG. Okay, so in this case here, so here a bit careful. I would say that if k is infinite, because if you go to a finite characteristic, there will be something equal 0. Algebraic close. Okay, thank you. If you take algebraic close view. Well, there's another very simple one. If we take ideal of a point, right? How about ideal of a point? It's just the ideal generated by x1 minus a1, x2 minus a2, and so on. Okay. For all a1 up to an in. Okay, so let's go a bit advanced here. So if you start with any subset of points here, we could consider I of x, and then we can consider the z of this function here. Okay, so you can ask the question: do I go back to x or not? I go no. 加一 why? Can you say louder? Then so you mean x, if x is not algebraic set, then this is not equal to x. Do you have an example? Okay, you can try and think about it. Maybe you can let me know later or after class. You can send me. Okay, so well, obviously, x will satisfy all the function to be 0 because that's how you pick your function. But potentially, you could have more things there. Okay, later I'll show you one example. And when is it equality holds? So it will hold when if and only if x is an affine algebraic set. So meaning you started with an algebraic set here. Okay, so similarly, based on C, right, we can play a different direction of game. Okay, so what's the different direction of game? You start with polynomial. Okay, if you start with polynomial, what can you do? You can ask about the 0. After you ask about the 0, you can ask about the ideal that give you the 0. Okay, then again, we have x is a subset of this set here. Not necessarily equal. Okay. Actually, this last line here, motivate the Hilbert Nullstellensatz. So what do you really get? What's the idea you really get when you do this construction? Okay, so let's try and prove them. Wait, let's try and prove them. So A and B, just leave it for exercise. Easy here. Well, by the way, if I put this kind of easy, trivial, obvious, whatever, try and write down the argument yourself, okay? If you cannot write it down, try and look for me. Try and come and find it, okay? And then, so this working also will be, hopefully, I will be put into the typesetted lecture note. So if you can help, right? So maybe you can provide the solution. Yeah, hopefully. Okay, ideal case. All right, let's prove C. Yeah, let's prove C. So what is C? We want to show that x is in the zeros of Ix. Okay. So any idea? Okay, I think we have another line, right? With equality if and only if x is already an algebraic set. What is Ix? So since Ix is defined to be the set of all function, okay, vanishing at all the points of x. So you can do a sanity check that this Ix is really an ideal. Okay, try and check that it's really an ideal. Okay, based on the property it has. That is Fp equals to 0 for all p. So if this is true, then what? Well, then I just turn the sentence the other way around. Then for any point of x, all the function must vanish. Vanish at ix. Okay, so in this case here, the point in x is always a subset of the 0 of ix. Okay. Okay, so let's prove this equality here. So if this this subset inclusion here is equality if and only if x is already a algebraic set. So meaning x is a z of some self-polynomial. Okay. Next. So this is first part. So second part, we'll say that x equals to z of ix if and only if x equals to z, let's say t for some t, which is a subset of the polynomial. Okay, so there are two directions here. So let's go from left to right first. Okay, we go from left to right. So suppose that x equals to z of ix. Okay, suppose that x is equal to z of ix. Then what? Is it an algebraic set or not? Of course. Why? So you just choose your t to be ix. Okay, here. Where do you find ix from? Ix live in where? Live in an. So this is the t you want to find here. Okay. I mean, for this kind of argument, you don't even need to know what is ix. You just need to know where if live. You understand what I say or not? You don't need to know where is common 0 also. There's no algebraic geometry content here. I just say that if x equals to z of something, how do you write z equals to something live in some space? Fair enough. Then we just choose e to be ix. Okay. Like this kind of problem, I can easily give to a discrete math student. I don't need to introduce the context one. No need to know what is common 0 one. Fair enough. I just need to tell you I need a subset from some data. Okay, there's no algebraic geometry content here. Yeah. How about the other direction? So we suppose that x equals to zt for some t in your polynomial ring. Then what? How do you relate to ix? What's the relation between ix and t here? Other than that, other than living in the same space, both vanish at a point x, right? Okay, but which one greater? I mean, which one is a subset of which? Then ix should at least contain t. Correct. Ix is an ideal. T is just maybe a finite set of polynomial. Correct. Does it make sense? But you see, this Ix contains T already. And Ix is an ideal. So meaning what? The ideal generated by T, you go and do the close under addition, close under scalar multiplication. Then it's also living inside Ix. Okay, so this also implies that Ix contain the ideal generated by T. Okay, so what did you see here? So we use the previous lemma, right? Do we call it lemma? We call it proposition or lemma? Position, right? Yeah. So by part A, right? What do you have here? P of Ix contained in Z of the ideal generated by T, but obviously this is equals to ZT, but ZT is just X. Okay, so we produce the other direction. Huh? For you one V. Oh yeah, sure. So one is okay. So here we put that. Okay, so we purposely put Z or V there. Sometimes we swap, but okay, there's one principle. Inside one paragraph, at least we want to be considered. But why we choose to put both of them together? I want you to abstract the idea. I don't want you to keep your focus too much on the symbol. So whenever I put Z, put V, what you should think about is a zero or something. Not about the Z, not about the V. It's about the zeros. Okay. Yeah. Okay. But one principle we need to try and keep it. Within one paragraph, we should keep the same notation. Okay. Yeah. All right. D is similar. D is similar thing to do. So D is similar. Very similar idea. So let's give some examples such that the inclusion could be strict. So let's look at this one. For example, in D, can you look at D here? The inclusion in D could be strict. So what is D? Let's bring the D down first. As in the ideal of Z plus. Yeah, let's try this. So let's suppose that our field is not algebraically closed. Okay, it's not algebraically closed. Then what do we want to play around with this kind of field? So we just get a polynomial. Get a polynomial. That is non-constant one. Be a non-constant polynomial that doesn't have a root in K, because this K is not algebraically closed. Having root. Root. Okay. In particular, so let's consider the ideal J generated by F. Okay. So first of all, here it is not unique, right? Okay, it's not unique, so for sure J is not the whole ring. It's not unique. But if you look at the zeros of J. Where's the zero of J here? So it's all the point in A1, because we just consider one variable polynomial here, such that Fp equals to 0. Okay, if it doesn't have a root in K, right, meaning nothing solve it. Okay, when you make it equal to 0. So meaning what? Meaning that actually this is that nothing solve it. Empty. Okay, so this is empty. But if you look at the I of empty set, right? Just now we talked about I of empty set, right? What is the I of an empty set? Everything. Okay. So Kx here. So we have a, so hence we got the ideal generated by J is actually a strict subset of Kx. Okay. So this is one of the examples. Any question? Any question? Okay. Okay. Corollary here. So, since we know that the ideal of a Noetherian ring over a Noetherian ring, you have ascending or descending? Ascending, right? ACC, ascending chain condition. Okay, so you have a ascending chain condition in the ideal. Okay, but if you apply Z to it, right, what happens? Z is a inclusion reversing property. So you will have an ascending chain become a descending chain. Okay, so you can translate the ACC condition into a descending chain condition in affine space. Okay, so the algebraic subset will satisfy the descending chain condition. Okay, so that is every chain such that descending, how to descend? So getting smaller. So getting smaller. Okay, getting smaller. Ascending getting larger, descending getting smaller. Right. So S2 containing S1, S3 containing S2. Getting smaller. Can you forever getting smaller or not? Your algebraic set getting smaller. 里面还有一个 cannot. Okay, so it cannot. So eventually stop. I think this is your intuition with your Rn. Okay. Okay, so how to prove this? You apply I to this thing, and then you will see that in the ideal case, you have an ascending chain condition. It must stop. Okay. Okay, we still got time, huh? Let's continue. Before we introduce Hilbert Nullstellensatz, we still need to do some more preparation here. So next lemma. So this lemma is quite technical, but very interesting to play around with this lemma. So if you have a subset of affine space here, which is an irreducible algebraic set. So in this case here is affine variety, but we will focus on this irreducible algebraic set here. If you found that this x lie inside union of some xi, where Si up to Sr, all these guys here are algebraic, also algebraic set. Then we said that irreducible is like a building block, right? So actually, this guy should live entirely inside one of the xj. Okay. Can think about how to prove it. It's about topology statement here, topological property here, not about algebraic geometry. If it lives in more than 2 hours, irreducible means what? Cannot split into two proper closed set. If it sit inside two algebraic set, what happened? You somehow split the x into two parts. What are the two parts? X intercept Sj, X intercept Xj prime. Yesterday we proved that intersection of algebraic set is still algebraic. Okay, then you will split it into two parts already. Right. Okay. Yeah. Should I write down? Okay. Okay. Any question or question first? Any question? Oh, can you follow? Cannot follow. Cannot follow. So let's go backward. Okay, back until where? Tell me. Back until where? 不可以每次从头，你知道吗？一直从头啊，代表没有什么听我在讲啊，因为这样沟通不太顺畅啊。对，我可以从头，希望不要每次从头啊，至少听到卡一半，你就要开始问了，可能要求你专心一点了，maybe。我知道我本身也是会来听 seminar 的时候会乱讲东西but try to 训练自己啊。Okay, so let's write down the proof. What do you need to think about here? 第一个，可能你要有一点想法哦。你的想法是 irreducible set。什么是 irreducible? Cannot be written into union of two proper closed set. Okay. So there are a few ways to prove this. You can use a contradiction, contrapositive, and so on. So let's prove it. So since x is in the union of this Si, right? Then really we can write it as x equals to the union of x intercept xi. Okay, but we know that x intercept xi are close, like what we proved yesterday. So if take two algebraic set and then intersect together, still an algebraic set. So it's close. So by irreducibility, right? You write x equal to union, but irreducibility says what? Cannot written as a union. So it must be equal to one of the intersection. Okay, so this implies that x will live inside xj. Okay. X is equals to x-intercept with something. To recover X, right, you should live inside Sj. You can prove this. I think this is a set theory proof. Okay. Right. So before we finish, break for the next part, let's mention some proposition. One proposition is an algebraic set X is irreducible. Is irreducible if and only if the corresponding ideal is prime. Okay. A set is irreducible if and only if the corresponding ideal is prime. So this gives you a condition how to check algebraic set is irreducible. How do you know you cannot split your algebraic set into two proper closed sets? One way is look for the ideal, okay, that define this X here, and then check whether this ideal is prime or not. Okay. And the other way around. Okay, if the ideal is hard to check, maybe you can see whether there's a algebraic set defined by this ideal. Okay. And the second one is any algebraic set X. Really, we can break it, okay, as a union of these irreducible. So meaning the affine variety. Okay, such that this xi is irreducible. So how is it a building block here? There's a unique way to build it. So what kind of unique way here says here? So these xi, right, and sj cannot be contained in each other. Okay? Cannot contain in each other. Maybe they will have some intersection, but cannot contain in each other. Cannot. And then xi are called the irreducible component of X. Okay, so later we'll present a proof for B, and the proof of B is the kind of standard proof to prove something that you have a unique decomposition. A kind of standard way to show it. Okay. Okay, so let's take a break until 5:05. Let me check who is not here. Ivan not here. Ivan, there. Hanwei not here. Hanwei disappear for 3 class already. Hey, Hanwei is in which group? Your group? Is your group member okay? No. Got meeting or not, you guys? When? Huh? Last Thursday. This week? Still meeting? Also Thursday. Okay. Thursday holiday or? Still meeting? This Thursday is holiday. Do you guys know? Yeah. So there's no topology class. Thursday is a holiday. Hey, Joel not here today. Not here. Okay.
晚上哦，上。要我累，我就这样。整天在听，要不是给这个，不是给那个老师，然后我要再去要做晚上。
什么情况？
旁边有一定的学校，可以问周末来学校。
做功课哦。
学生还要来照顾。
耶。嗯嗯，
要来有人讲课，我之前讲课没有。
他没有想这样多，他要你吧？他没有想这样多，他要你吧？
不要讲，
是呢，这样你的 existence 让他有安全感。Cannot find you, just exist。我也是问同一个问题。
他们在熬夜啊。
对，他熬夜还是没有熬夜？他昨天去吃妈妈。哦，他交了。不懂。是吧？ 很爽，什么意思？OK，嗯，他没有给你答案，他给你答案。哦，之前给你答案，什么意思？嗯哼，嗯，OK OK，嗯嗯啊就嗯，看你绝望，你这么绝望，你绝望什么？他希望太高还是你？你说他会绝望呢，还是什么啊？然后什么意思啊？什么东西没有想象中那么好玩？哦，study group 哈，OK 啊，我觉得还好啊，我觉得不错，其实我觉得不错。Okay, hello, let's continue. Okay, let's prove these real quick here. So, algebraic set is irreducible if and only if the ideal defining this algebraic set is prime. So instead of proving that, we will prove the contrapositive. So meaning if x is reducible, if and only if ix is not prime. Okay, so why we turn into this kind of statement? Because if you turn into reducible, meaning what you can write, you have something to work with. Okay, you can write it as a union of two proper set. Ix is not prime means what? What's the negation of prime? Prime is what? AB in A implies A in A or B in A. So the negation is A in B not in I, AB is not in I. Okay. Okay. Let's do this. So two direction. Left to right, right to left. So if we do left to right, then suppose you can split your x up with algebraic set or subset x1, x2, x. Okay, then in this case here, what do you have? Then you have two proper subset, right? X1 in X proper and X2 in X. So meaning what? If you look at I x1 and ix, what's the difference here? Which one have more points from last hour? You have subset inclusion, right? So ix is in ix1. Okay. So if you take out all the ix from ix1, you should be able to find some polynomial here. Okay, similarly, there's this f2 such that ix2, sorry, f2 is in ix2, take away ix. Okay, but now if you look at f1, f2, what does f1, f2 do? This product here will vanishes at all points of x. It will vanish at all points of x. So meaning what? So F1, F2 actually live in the ideal of Ix. Okay. Therefore, Ix is not prime. Okay. So meaning you can split out an element into two elements that both don't live in the Ix. Okay, because if it is prime, then one of them must live in Ix. Okay, so this thing really important. So irreducible algebraic set correspond to a prime ideal. That's very important here. Okay, how about the other direction? Suppose Ix is not prime. Okay, not prime means what? So same things, we kind of work backward. So there exists F1, F2 not in Ix, such that their product is in Ix. Okay, so what's the trick here? I think it's really similar how we come forward just now. So we kind of go backward. So we'll look at I1 that is generated by Ix, comma F1, and we let I2 to be Ix, ideal generated by Ix, comma F2. Well, we can look at their zero set. Let's use V here. Okay. One clear thing you should see is clearly X1 is in X and X2 is in X. Okay. Otherwise, the assumption is false. Meaning you cannot find such F1, F2. Okay, if you can find it, that means you have some point that's not in X1, X2. In X1, X1, X2. But what do you see here? Actually, but what you can see is X is in the union of X1, X2. So how do we prove this? We just need to show that every point in X satisfy the zeros of I1 and I2. Okay, so let's check it. So since for every point in X, okay, what do you have here? F1, really you just need to check F1 times F2. Okay. F1, F2 on P is what? Is F1P and F2P. Okay, equals 0. Okay. Y equals 0. Okay, so maybe I think this equals 0 part should be put on the other side. Okay, on this side. Right. So F1, F2, P must be 0. Is it true that F1, F2, P must be 0? Or the other way around? So, well, you see, so where's the assumption here? So let me put this assumption here. So actually, we are using this assumption here to say that F1, F2, P is 0. But F1 times F2 on P is just F1P times F2P. Okay, this implies what? Camping. What does this imply? Two things multiply together to get 0. Yeah, one of them is 0 because we are working on the integral domain. So either F1P equals 0 or F2P equals 0. Okay. So meaning it is lie inside one of the xi. Okay. So we can conclude that x equals to x1 union x2 because the other direction is obvious. It's because how we pick these s1, s2. Because they are the subset of x, the union of them still a subset of x. Or we just need this direction. Okay, so as desired. Okay, so this is about prime and irreducibility. Next part, we're gonna decompose, okay, our algebraic set using affine varieties. Okay, affine varieties. So what do we do here? It says that everything can be decomposed, right? So should we use contradiction here? Let's see, yeah, so I think we're gonna use contradiction. So let's let sigma be the set of algebraic subset of an, which does not have a decomposition. Okay. So if this set is empty, right? There's nothing to talk about. There's no uniqueness you can discuss about. There's nothing to talk about here. On the other hand, if there's something there, we're going to show that it should have a decomposition. Okay, so if there's something that you cannot write as a decomposition by the previous corollary, there must be so which corollary we are using here? There must be a minimum element here, okay, through the descending chain condition. Okay, and again, this will lead to two contradictions. So let's see what's the two contradictions. It's to one of the two leads to one of the two contradictions. Okay, so let's see what's the contradiction here. Well, if x is irreducible, then it shouldn't be inside the set here because it is just equal to itself. Okay, so this is the first contradiction. Second contradiction here is if x is reducible. Reducible means what? Lydia? S can be split into, yeah, can be split into what? Union of two proper closed set. Okay. But you see, you split into two proper subset. Meaning what? S1, S2 should be smaller than X1. But how do we pick this X here? It is the minimal one. Meaning what? So these two of them, right? These two of these X1, X2, right, shouldn't live inside the set that has decomposition. Because X is already the minimal one. You found a smaller one, even smaller one. This smaller one shouldn't live inside the sigma anymore. Because otherwise contradiction to this X. But doesn't live inside sigma means what? Sigma say everything that doesn't have a decomposition, right? So this one live outside sigma, meaning what? This guy has decomposition. So each of xi, x2 has a decomposition. As an union of irreducible. So what can you do here? You know x is equal to s1 union s2. You know the decomposition of x1. You know the decomposition of x2. Then you just put all the decomposition together. Then this is a decomposition of, this is a decomposition of x. Together, this is the decomposition of X. Meaning what? X has a decomposition. So X shouldn't be in sigma, contradicting the construction of X. Okay. Okay. No? Okay. So you see, although the point we use here is the descending chain condition, that part needs commutative algebraic geometry. But when we put all these points together, really, I still can throw to a discrete thing. You understand? Once I tell you all these points, you just put these points together. This is just a contradiction to some minimal and the existence of minimal object. Does it make sense? Okay. Yeah. Just the XCC part, we are using some commutative algebra and the zero set property. Yeah, other than that, it's just logic, pure logic. Yeah, yeah. What? Oh, thank you, thank you. Yeah, not easy. Okay, so this gives the existent part. Okay, so how about uniqueness? Uniqueness is also kind of a standard thingy here. Okay, so this uniqueness here will use the lemma we proved just now. So let's see how it goes. So uniqueness, right? So let's say we can split our X into two ways. Okay. One is X1 up to, let's say, SR. The other one is Y1, Y2 up to YX, let's say. We don't even know whether this R and X is the same or not. Very general. Okay. But we know that each of them should be irreducible. Okay, so this is what the statement gave you. We want to split them to be an irreducible one. Moreover, they cannot contain in each other. Probably they could have an intersection, but they cannot contain to each other. Okay. But what's the key here? What's the key here? Okay, the key here is if we use the previous lemma, so meaning if you have an irreducible living in some union, you must live in one of the component. Okay, so in this case here, what you can see here, by previous lemma, for every I, okay, Si will live in one of the ij or some ij. Okay, so similarly, every ij, for every j, ij will live in some, let's say, I naught. Okay, so the claim is this two is enough already. Okay, this two is enough. Why is it enough? Not that if we try to put them in a chain, Si is living in some Yj, and then this Yj is living in some Xi0. What do you get here actually? Huh? Say again? They're too far, you know, here. Can you say it louder? I0 equal to Iy. Wait. So, okay, so the claim is, so let's put down the claim. The claim is Si equals to Xi0 equals to Yj. Obviously, if those two are equal. So if Xi not equal to Xi0, what could happen? It's reducible. Yeah, you should use irreducibility. So how do you use it? Yeah, you should use the irreducibility here. Hey, this one is logic, not logic. Okay, it's logic. So lemma we proved just now. If xi live in the union of, okay, if x live in one your union of xi, right, then x must live in one of the xi. But this xi, this particular xi here, is live inside a union of sj, and then it must live in one of the huh? No, no yj. We're talking about sj now. We go back to sj again. Okay, should I write it down? Yeah, let's write it down. So xi live inside the union of some sj, right? If it doesn't equal to one of the sj, what happens? You got a new irreducible inside here. Okay, so it must be one of the sj. Which one? It already live inside xi naught. It should be that one. Okay, otherwise you have a new irreducible. Okay, so it should be that xij. Okay, due to the irreducibility. Okay, so therefore, every xi will correspond to one of the yj. Okay, and vice versa. So that you can get the same number on both sides. Okay. Okay, let's look at some example then. How we split out algebraic set. Okay, so suppose that we have a function that is f1 to some power up to the product of fi to some power. Okay, then what do you reckon on this zero set here? How to make this function zero? How to make this kind of function zero? One of the factor equals zero is enough, right? But more than that, I just need to make one of the fi zero is enough. Actually, you can show this. Okay. Okay. So in this case, if we have more condition here, let's say this K is algebraically closed, then actually this is the decomposition. Okay, so meaning all these are irreducible. Okay, in this case here, you can ask so you can ask a question. If I go I on this VF, what do you get actually? What function get killed under this point here? Actually, it's more than the ideal generated by F, you know. You could look at the ideal generated by F1 multiply up to Fn. Alright, you take a point here, put it here, evaluate it, you get 0. Okay. You can see that, hey, we're kind of taking square root of this. I mean, not square root, root of this, radical of this function. Radical. Taking some root of this function. Okay. Actually, this example will motivate the next part later. Another thing, let's see which thing to discuss here. Let's discuss this example. So let's consider the zero set of x squared plus y squared times y minus 1 squared. And let's discuss about this in R2. I mean, this zero set, how do you determine here? You want to make this zero, but inside these sum, these are all positive or non-negative number. So the only way to make this zero, what do you need to do? Make the term zero. Both terms have to be zero. But to make x squared to be zero, what do you need to do here? Zero. Okay, you could only take x to be zero. But why? There are two choices, right? There are, well, two roots here. Either y is zero, either y is 1. Okay, so actually there are 2 points only in R2 that satisfy this. 0, 0, and 0, 1. So in this case here, well, 0, 0 define an affine algebraic set, right? And then 0, 1 also define an affine algebraic set, which is one of them is x times y. No, x comma y, right? And then the other one is x comma y minus 1. Okay, you want these two to be 0 at the same time. So really, you can say that x is reducible. Okay, because you can write it as the union of the origin and the union of, and then these are the v of the ideal generated by xy, and then the other one is v of the ideal generated by x and y minus 1. Okay, so this is reducible, but this function here, fxy, is it reducible or not? But this function, yeah, so it's reducible, it's irreducible in R actually, but it's reducible in C. So what is the factor here? Oh, let's write down is x plus iy times y minus 1 times x minus iy times y minus 1. Okay. So in this case here, this is when we view it in C adjoint x1. Okay, we change the scalar field, okay, to complex. We need this complex number here. Okay. So well, if you say that this factorization could be done in C adjoint y, right? But we know that R adjoint, sorry, C adjoint xy, but we know that R adjoint xy also live inside C adjoint xy here. And they are UFD. They are UFD. So meaning what? So if F factors in Rxy, then the decomposition must agree, right? Agree up to some constant multiple, some unique, right? Some unique. Last time we proved, right? There's a unique factorization into primes. The decomposition we had up to constant multiple. Okay, but this is impossible. Okay, so this is to prove that the function is irreducible in R adjoint xy. So what's the difference between R adjoint xy and C adjoint xy? So C is algebraically closed. Okay, R is not algebraically closed. Okay. So sometimes we'll prefer to work in algebraically closed field so that the reducibility properties will compatible with the geometry. Where the ring side and the geometry side will coincide. Okay, otherwise they will behave different. Okay. All right. So this will motivate the next part here. Okay, good. We got plenty of time. So first thing to motivate here is we will define what is called a radical ideal. Okay, so just now you see that we just look at the ideal generated by the radical of your function, okay, to get the original zero set. So if I is an ideal of an, then the radical ideal, so which we written as red I here. So the natural, the conventional notation is square root I. No matter what power you take, we just call it square root I. Okay, symbolically. So what are these? These are the f in the polymer ring such that f to the power some n is living in I. Okay or not? So if you are some power of f living I, we just take the f. Like what we did just now. Okay. This is like in the n root form. You take fn, then you take n root because n. That's why you put it into the radical ideal. So in case I equals to red I, okay, so meaning for all the power of f living in I, f is also living in I, okay, then I is called an radical ideal. Okay? So meaning for all the powers of function living in I, its roots also living in I, then this ideal is called radical ideal. Okay, radical ideal. So since I define this as an ideal, right? So first thing you should check is whether this red I is an ideal or not. So let's check. Let me check. Square root I is an ideal. Okay. Is it an ideal? Huh? I think multiplication is easier, right? Yeah, if f is living inside this ideal, meaning f to the n is living in this ideal. So you need to ask yourself, if f live here, rf live here or not? If rf live here means what? R to the power n, r to the power f to the power n also live in I. But I is an ideal, right? Obviously, that's living in I. But more tricky part is the addition part. So if f and g live inside this red I here, meaning what? Maybe there's some n such that fn living inside I and gm living inside I. But the problem now is you need to argue that f plus g live inside red I, meaning what? F plus g have to have some power raised such that it lives inside I. Given that you know fn and fm live inside I, can you guess what power you should take for f plus g? One. Common notorious question. What do you think? Huh? mn? What do you mean? Take m or take n? Take m or take n? You think first, let me write down what do you. If fg in red I, so meaning that there's this nm such that fn em live in I, then what's the, let's say we call it r. What's the r we should take here? What do you need to imagine here? If I take this power of r, right, meaning what? I do a binomial expansion. So you need to make sure that every term live in I. But what do you know? You know fn and gm live in I. So each of this term must at least contain as large fn and as large fm. So which power you need? Huh? M plus n. Okay, actually, Sorry. Okay, so let me write down binomial expansion formula first. Actually, you just need r greater or equals than n plus m minus 1. You can try and expand this term here. Use n plus m minus 1. Try and expand this formula here. Okay. And then this will guarantee that every term will have either fn or fm inside there. At least. Okay. You got it? You got it? How do you got it? Okay.
So either one must be larger or equal to n, or the other must be larger or equal to n.
Okay.
Each of the terms will have part of it that was in the ideal, therefore the term will be.
Okay. So if you still cannot follow what he said, expand it. Go and expand it. This is where you need to do maths. Okay. No? This is where you need to do maths. Expand it. I gave you formula already. I gave you number already. Go and expand it. Okay, then you will see. Okay. Either this product will contain Fn or Fm. Okay, or greater, the degree greater than Fn. Okay. Next. So I got 10 minutes. So one thing you can show is prime ideals are actually radical. Okay, prime ideals are actually radicals. Is it hard to see or not? Not hard to see. I Ehang try. Not hard to see. Well, which direction is easier? Maybe let's see. So let's call our prime ideal J. Which one is easy? J in red J or red J in J? Huh? J in red J is easy? So J in red J means what? The radical of J must live inside. I mean, okay, we haven't defined radical of function, right? So, okay, well, should we do this together? Okay, at most 5 minutes. So, if I take a function in J, okay, what do we need to show that it's in red J? Huh? What do you need to show that F is in red J? I'll see you on the try. Red J definition. There exists some n such that Fn is in J. What's the n you can take here? 1. Okay, how about the other direction? Take F in red J. Meaning what? It exists some power of Fn in J. But you want F in J. But J is prime. J is prime means what? If you split it as a product of two things, one of the things must live inside J. But Fn, how to split? Depend on you. I don't care how do you split. You want to split n minus m times Fm also can. Either one of them must be there. But you split until the end, you sure will get F1. Okay or not? Okay, so sorry? What? Oh yeah, also well, I mean if it is the case that okay, I don't know. I mean like in general, we don't know which one is in there yet. If you split into Fn minus 1 and F either Fn minus 1 is in there or F is in there. If F is in there, you're done. Sure. Yeah. So what I wanted to say is you cannot avoid the general argument. Yeah. Because we don't really know whether F is in there. Okay, we just can split. So either Fn minus 1 is in J or Fm is in J. Then you continue, okay, with the prime element. In the end, for sure, or finger cross. Okay, so prime will imply that F is in J. Okay, for sure you will reach F. 第一次遇到它还没有抓到它，不用紧，再继续做，做到最底，它一定要出现的。OK 吗 ？Yeah， 第一次抓不到它不用紧。Okay, I think we don't have time to prove it, but we're gonna state it properly. Okay, we're gonna understand it properly before we prove it in the next lecture. So this is Hilbert Nullstellensatz. Actually, it's called the Hilbert zero theorem here. Nullstellensatz is a German word. Yes. So let K be an algebraically closed. So you see, just now we got a case that's not algebraically closed, right? There's some issue that the ring part and the geometry part doesn't quite match up. So now we just restrict ourselves to algebraically closed field here. So that's also the reason why you see some of the text just restrict their field to algebraically closed. They want this Hilbert Nullstellensatz to hold. Okay. So for this to hold, you will need an algebraically closed field. And then first thing you can prove is there's a correspondence between points and maximum ideal. Okay, so meaning what? So if you consider a subset of your affine space, okay, this is the affine space. Okay, sorry, no, this is not the affine space. This is the polynomial ring, okay, of n variables. And if you look at the maximal ideal, okay, all the maximal ideal that contain, okay, that contain this subset S, okay. Obviously, this ideal contained in polynomial ring. So there's a one-to-one correspondence here. So what's the one-to-one correspondence here? Then, if you look at the zero set of this subset of polynomials, okay. So there's a bijection between the maximum ideal. Okay, so meaning what? You just send each point to the, what's the maximum, obvious maximum ideal here? Using the division algorithm thingy. Okay, so this is just x1 minus a1, comma, up to xn minus an. Okay, last time we proved that this is maximum. Because if you take the polynomial ring, polynomial ring looks like an affine space. Get rid of this. So if you take this ring portion by this ideal, right? What do you get? You will get the field. It's the evaluation homomorphism. This is the kernel of the evaluation homomorphism. So how do you remember this kind of ideal is maximal? It is the kernel of the evaluation homomorphism. What's the evaluation homomorphism? Send the xi to ai. Then you kill all the polynomials. After you killing all the polynomials, what do you get? You left with the field. So okay, then this is the kernel is equal actually. So equal to that kernel. So there's a bijection between these two sets here. Okay, actually this is the last thing we left in AA1, right? Before we finish. So this is the last part we left. We talk about this. Huh? Yeah. Okay, so this is the part that I mentioned that there's a connection to algebraic geometry on the maximal ideal. Okay. Next statement is the weak Nullstellensatz. Okay, so we basically split Nullstellensatz into two parts here. So first part is called the weak Nullstellensatz. So what's the weak Nullstellensatz here? Maybe this statement is kind of obvious. Okay, we'll write it down. If you take a subset of polynomials, okay, and then if you look at the zero set, okay, the zero set of this ideal, such that it's empty, what do you think this I should be? Can this I be anything or not? Or ask you another question. Last time we said Z of what is empty? Z of what is empty? AN, right? Everything, right? But now the question is, apart from AN, does any other set will give you an empty set of 0 or not? The weak Nullstellensatz tells you that only AN will give you this empty set of 0. Okay, turns out to be quite technical to prove. Not technical, but yeah, actually quite technical, using a quite strong statement, but the argument is not too complicated, but using some strong statement. Okay, and then the last one is the, since you have strong, right, you must have, sorry, since you have weak, so you must have stronger. Okay, the last one is a strong Nullstellensatz. Huh? 没有 middle. What's middle? Between weak and strong is what? Average. Yeah, I don't think people use average much for interesting adjective. Okay, never mind. So what's the strong Nullstellensatz here says? So for every ideal, okay, for every ideal in A, what do? Look at the 0 first, and then go back to ideal again. What do you get? It's not J. Just now we said that could be a subset. J could be a subset of this, right? But to show equality here, what you need to put, the right guy to put here is square root of J, which is the radical of J. Okay? Kind of makes sense, right? Just now I show you the example, product of Fi, product of power of Fi. If your point vanish on those functions, it should already vanish on each of the Fi. Okay. Turns out that this proof is quite hard. This proof. There are different versions of this proof. So there are very technical one using Grosvenor basis stuff to compute. But we're gonna use a trick called I think I forgot the name. Start with R. What's the name? Rabinowitz. Okay, Rabinowitz trick here. Okay, to prove this. It's rather straightforward. And I put various proof on the Google. You call it. Okay. And then next week we will discuss about this. Okay. All right. See you next week.